What is the path of a charged particle when it enters a magnetic field perpendicularly? Let's see what that looks like. Here I have a positively charged particle on the left, and it's moving from left to right, and it's going to enter a region on the screen where there's a magnetic field going into the screen. So the charged particle is in the plane of the screen, and the magnetic field is perpendicular to the screen, so they're moving perpendicular to each other. The question is, what's the direction of the charged particle when it enters that region of the magnetic field? Think about it and take a guess. Hopefully you've thought about it a little bit. Let's see what actually happens. Here's the positively charged particle, enters the magnetic field, and whoa, it's curved, like circular motion curved. So it's going up. So there's a force acting perpendicular to the velocity. So a charged particle entering a magnetic field, that's a Lorentz force, or the open right-hand rule, where my thumb is the direction of the positive charges, fingers of the field going into the page, my palm is the push or the force pointing to the center of this circular motion. Let's see what else we can think about and figure out. So I've got going in a circular motion, that means I'm going to have a centripetal force, and every centripetal force needs a source. The source, in this case, is going to be that charged particle moving through the magnetic field, or the Lorentz force. So in other words, mass times the centripetal acceleration is equal to qvb sine theta. Now if I think about it a little bit more, in this particular case, the velocity vector and the magnetic field vectors are perpendicular to each other. So their angle between them is 90 degrees. Sine 90 degrees is 1. So this qvb sine theta becomes qvb. And with the circular motion, MAC, well, the AC, we can represent that with v squared over r. That's the velocity squared divided by r. So now making that substitution, that gives me mass times v squared over r is equal to qvb. And a helpful relationship is actually to isolate r in this equation. And if I do that, I get that the radius is equal to the momentum divided by qb. So the radius of the particle is equal to the, is directly proportional to the momentum of the particle, and the radius is inversely proportional to the charge and the magnetic field. Now, when determining the direction, whether it's going to curve up or curve down, that's when you have to physically use your open right-hand rule to go through the motion to decide if it curves up or curves down.